Hello everyone, this is Akash, a student of RV College of Engineering from the Department of Aerospace. I am here to give a presentation on the topic polymers for solar cell applications. Firstly, let us address the question of what is a polymer. A polymer is a substance or material consisting of very large molecules or macromolecules composed of many repeating subunits. We can see polymers every day in our day-to-day lives. We use polythene bags or water bottles, fiber, which consists of our laptops are all made of polymers. A conjugated polymer is formed where carbon atoms covalently bond with alternating single and double bonds. Here I have shown you a widely used conjugated polymer, that is PANI, that is polyaniline. Solar cell is a device that directly converts the energy of light into electrical energy through the photovoltaic effect, and you can see the picture here. These are also not new to us, as we have solar water heaters on our terraces, and solar farms which are used to produce electricity for domestic purposes. When polymers are used in making solar cells, they are called organic solar cells, which will be a further discussion. An organic solar cell or plastic solar cell is a type of photovoltaic that uses organic electronics, a branch of electronics that deals with conductive organic polymers or small organic molecules for light absorption and charge transport to produce electricity from sunlight by the photovoltaic effect. Some commonly used small molecules and polymers in organic solar cells are shown here: polyacetylene, polyphenylene vinylene, PPV, phthalocyanine, MEH-PPV, which stands for methoxy-ethyl hexyloxy polyphenylene vinylene. Compared to silicon-based devices, polymer solar cells are lightweight, potentially disposable and inexpensive to fabricate, flexible, customizable on the molecular level, and potentially have less adverse environmental impact. Polymer solar cells also have the potential to exhibit transparency, suggesting applications in windows, walls, flexible electronics, etc. In organic semiconductor physics, the highest occupied molecular orbital of the conjugated polymer takes the role of the valence band, while the lowest unoccupied molecular orbital serves as the conduction band. The band the band gap of organic electronic materials is typically in the range of 1 to 4 electron volts. Organic photovoltaics can be fabricated with an active polymer and a fullerene-based electron acceptor. Illumination of this system by visible light leads to electron transfer from the polymer to a fullerene molecule. As the result, the formation of a photo-induced quasi-particle or polaron occurs on the polymer chain, and the fullerene becomes a radical anion. Polarons are highly mobile and can diffuse away. All light with energy greater than the band gap of the material can be absorbed, though there is a disadvantage to reducing the band gap, as photons absorbed with energies higher than the band gap will thermally give off their excess energy and lower the output voltage, and power conversion efficiencies will also be lower. When these materials absorb a photon, an excited state is created and confined to a molecule or a region of polymer chain. The excited state can be regarded as an exciton or an electron hole pair bound together by electrostatic interactions. The different types of junctions in polymer solar cells are single layer, bilayer, discrete heterojunction, bulk heterojunction, grid heterojunction, continuous heterojunction. Here you can see pictures of single layer and bilayer junctions. Single layer junctions are the simplest junctions. These cells are made by sandwiching a layer of organic electronic materials between two metallic conductors, typically a layer of indium tin oxide with high work function and a layer of low work function metals such as aluminum, magnesium, or calcium. Bilayer cells contain two layers in between the conductive electrodes. The two layers have different electron affinity and ionization energies. Therefore, electrostatic forces are generated at the interface between the two layers. The layer with high electron affinity and ionization potential is the electron acceptor, and the other layer is the electron donor, which has lower electron affinity and lower ionization potential. This structure is also called a planar donor acceptor heterojunction. Most widely used junction is a bulk heterojunction, which we will discuss in the next slide. Bulk heterojunctions have an absorption layer consisting of a nanoscale blend of donor and acceptor materials. Efficient bulk heterojunctions need to maintain large enough domain sizes to form a percolating network that allows the lunar materials to reach the hole transporting electrode, that is electrode 1 here, and the acceptor materials to reach the electron transporting electrode, that is electrode 2. After the capture of a photon, electrons move to the acceptor domains, then are carried through the device and collected by one electrode, and holes move in the opposite direction and collected at the other side. If the dispersion of the two materials is too fine, it will result in poor charge transfer through the layer. Most bulk heterojunction cells use two components, although three component cells have been explored. It consists of a secondary p-type donor polymer that absorbs light in different regions of the solar spectrum. This ternary solar cells operate through three distinct mechanisms. Charge transfer. In charge transfer, both donors contribute directly to the generation of free charge carriers. In energy transfer, only one donor contributes to the production of holes. In a parallel linkage, both donors produce excitons independently, which then migrate to their respective donor or acceptor interfaces and dissociate. Now let us see transparent polymer solar cells. Transparent or semi-transparent polymer solar cells allow for the absorption of low or high intensity photons outside the visible spectrum, thus optimizing its sunlight harnessing capabilities and covering a broader absorption spectra. These are ideal for capturing near infrared and ultraviolet photons due to its low inherent sensitivity to photons within the visible spectrum. When the top electrode is made transparent, the cell's ability to trap the electromagnetic field in the absorber layer decreases, resulting in low power conversion efficiency. An extensive amount of research is currently being conducted to improve the power conversion efficiency of such cells. Hence, these have been applied to building integrated photovoltaics, tandem devices, and portable electronics, and have stayed away from mainstream polymer solar cells. Here is the current voltage behavior of a polymer solar cell. JSC stands for short circuit current, which is the maximum photocurrent generation value. It corresponds to the y-intercept. VOC stands for open circuit voltage, which is the voltage when there is no current running through the device. This corresponds to the x-intercept. Since power is the product of voltage and current, the maximum power point occurs when the product between voltage and current is maximized. The fill factor FF can be thought of as the squareness of a current voltage curve. It is a quotient of maximum power value and the product of open circuit voltage and short circuit current. It is the ratio of area of yellow triangle to the area of yellow rectangle to the area of blue rectangle, which is shown here. Fill factor is essentially a measure of how efficiently generated charges are extracted from the device. Here is a formula for calculating power conversion efficiency. P where JSC is short circuit current, VOC is open circuit voltage, FF is fill factor, and Pin is incident solar power. Now let us have a discussion about commercialization of these organic polymer solar cells. They are yet to commercially compare to silicon solar cells and other thin film cells. The present efficiency lies near 10%, well below silicon cells. They also suffer from environmental degradation and lack effective protective coatings. Efforts are being made to upscale manufacturing of polymer solar cells in order to decrease costs and also advocate for a practical approach for polymer solar cell production. Therefore, commercial applications for polymer solar cells still include primarily consumer electronics and home appliances. Here we can see the number of publications that have come up each year for polymer solar cells, indicating that there is an extensive research being done on this topic. Let us see the challenges which prevent us from using polymer solar cells in day-to-day life. Charge carrier mobility and transport. The bulk heterojunction devices have imbalanced charge carrier mobility. This results in space charge buildup and decrease in fill factor and power conversion efficiency of a device. Effect of film morphology. Film morphology can also have a drastic effect on quantum efficiency of the device. Rough surfaces and the presence of voids can increase the series resistance and also the chance of short circuiting. Progress in growth techniques, mostly organic films for photovoltaic applications, are deposited by spin coating and vapor phase deposition. As each method have drawbacks, spin coating technique can coat large surface areas with high speed, but use of solvent for one layer can degrade the already existing polymer layer. Some of the solutions arrived at through research for these challenges are: film morphology and quantum efficiency can be improved by annealing of a device after covering it by approximately 1000 angstrom thick metal cathode. Controlled growth of the heterojunction provides better control over positions of the donor acceptor materials, resulting in much greater power efficiency than that of planar and highly disoriented heterojunctions. Thus, the choice of suitable processing parameters in order to better control the structure and film morphology is highly desirable. Polymer solar cells' inefficiency and stability problems, combined with their promise of low cost and increased efficiency, made them a popular field in solar cell research. As of 2015, polymer solar cells were able to achieve over 10% efficiency via a tandem structure. In 2018, a record-breaking efficiency of organic photovoltaics of 17.3% was reached via a tandem structure. With this, I would like to conclude by saying that polymer solar cells are very advantageous to us because they are very easy to fabricate. Isn't it exciting to think that in the future we might have transparent windows which we can open and close, and in the meantime they generate electricity?